All right, welcome to Physics Video 3.7. We're going to learn about just some more free body diagrams, a little bit more practice, and time permitting, I'm hoping, that we will get to terminal velocity. So hopefully we will have time to get to terminal velocity here. All right, so objectives. By the end of this video, you should be able to draw a complete free body diagram. You should be able to understand and apply the fact that all objects on Earth have a force of gravity, even if the object is sliding sideways. And then hopefully we'll have time to explain the concept of terminal velocity. So here we go. This was on the last video. I'm going to throw it up here again. If you didn't write it down in the last video, you should write it down this time. This last step, the third step, is the most important one. People always have a tough time with it. Remember, if you know the acceleration, then you should use Newton's second law to find the net force, and then find any missing forces. If you know all the forces, then add them together, add up your forces to find the net force. And then once you've got that, then work backwards and find your acceleration. You will see that in practice here in a few examples. So here we go. I'm going to do a few examples. So in this one, Ed lifts an 8-kilogram dog upward from rest. So draw yourself a dog, 8 kilograms. Remember, always start with your mass and your force of gravity. And remember, the force of gravity is 8 kilograms times -10, so it's -80 newtons. Okay. Now, Ed is lifting the dog upwards. So here's our force of Ed. It's 100 newtons. That's our second step, is write down any given forces. And then our third step is to either find the net force or the acceleration. So I need to think here. The dog is sitting on the ground, but Ed is lifting him up. So the question is this enough force to lift the dog? Well, since the dog only weighs 80 newtons, and we're lifting with 100 newtons, that's going to be enough to move him. So the dog is going to move. So there's going to be some acceleration. I just don't know what. So I don't know the acceleration. Let's find the net force. So to find the net force, I can add up all my forces, right? So in this case, it's the force of gravity plus the force of Ed. So it's going to be -80 plus 100 equals 20 newtons for my net force. So now I can find my acceleration. I've got a net force upwards of 20 newtons because I've got 20 more newtons up than I have down on an 8-kilogram object. That's going to give me an acceleration of 2.5 meters a second squared. And so now I should be able to find the final velocity. So Vf equals Vi plus At. Since he started out at rest, our Vi is 0. So you're going to get 0 plus the acceleration, which is 2.5 meters a second squared, times the time, which is 3 seconds. So we're going to get to a velocity of 7.5 meters a second. So my final free body diagram would have to have the drawing. It would have to have the net force and the acceleration and the velocity. So I guess that's it. All right. The big thing I want you guys to understand here is the force that determined the acceleration was not Ed's force. The force that determined the acceleration was the net force. Okay, that is going to become very important in the next example. Please notice that the only reason Ed was able to lift the dog is because the force he exerted here was more than the force of gravity. Okay, in the last video we saw what happened if Ed's force had been smaller than the force of gravity, which is it wouldn't move and the normal force would fill in the remaining force. Okay. All right, so this time we're going to work backwards. This time we've got a 30-kilogram box. So you're going to have a force of gravity of -300 newtons. And this time Carl is going to lift it. It tells you that, but it doesn't tell you how much force he's exerting. It does tell you that it's going to accelerate at 2 meters per second squared. So as a general rule of thumb, if I give you the acceleration, find your net force. So net force is mass times acceleration. We got a 30-kilogram box accelerating at 2 meters per second squared. Gives you 60 newtons. Now, remember, that is not the force that Carl is exerting. That's the net force. So the question is, how much force does Carl need to make this the net force? Some of you are able to look at it and just go, well, the net force is 60. That means there's 60 more newtons up than down. So if there's 300 down, there must be 360 up. If that's not immediately obvious to you, then use algebra. Your net force is the force of gravity plus the force of Carl. So 60 newtons is the net force. Force of gravity is negative 300. Force of Carl is what you're looking for. Add 300 to both sides, and you get 360 newtons equals the force of Carl. All right, so there you go. So then the velocity after 4 seconds, I'm going to skip this on a lot of these. To find your final velocity, it's just this, Vf equals Vi plus At. So you're going to get 0 plus, our acceleration is 2, the time is 4, so you're going to get 8 meters a second. V equals 8 meters per second. Okay, so there you go. All right, so now we've got a pony. It says Norm pushes a 160 kilogram pony. All right, so we've got a 160 kilogram pony. I just tried to draw a pony and failed, so you're going to just get a box. Here's our pony, 160 kilograms. You can always start with your force of gravity. So gravity is going to pull the pony down with a force of 160 newtons. So that's step 1. Step 2 is any given forces. There's the force of Norm pushing him to the left. Since we're trying to slide him to the left, oh shoot, I'm going to write out Norm here, because in a minute we're going to have a normal force. I'm mad that I chose the name Norm instead of Roy, which I usually do. Okay, so anyway, Norm is pushing to the left with 960 newtons. Friction is going to try to prevent the pony from sliding, so friction is actually going to be positive this time, 320 newtons. And we need to make a free body diagram after 2 seconds. So in this one, we've actually got forces in two directions, right? We've got up and down forces and left and right forces. So first of all, let's focus on the up and down, all right? Presumably the pony is sitting on the ground. It doesn't specifically say that, but I should have written the problem that way. So let's assume that he's sitting on the ground. So because of that, the pony's not going to move down even though gravity is pulling him down. There's got to be an upwards force to cancel out gravity. So our force of gravity is 1,600 newtons. Please make sure I had that wrong. I apologize. So our normal force has got to be big enough to cancel that out. Basically, what's going to happen here is this force cancels out this force and prevents the pony from moving up or down at all. There are, however, horizontal forces. So our net force is going to be the 960 newtons from Norm plus the 320 newtons from friction. Gives you negative, what's that going to give you, 640 newtons. And so now we can find the acceleration of the pony by doing net force over mass. So you're going to get an acceleration of negative 4 meters a second squared, which means, assuming that your initial velocity was 0, which it didn't say, I wrote this poorly, your final velocity is going to end up being negative 4 times 2 plus 0, so you're going to get negative 8 meters a second. Okay? The big thing to see here, we've done problems like this before, but the big thing to notice is that even though the pony's motion is this way, horizontally, you still have to take into account the fact that gravity is pulling it down and there's a normal force holding it up. Okay, so your free body diagram will have, in this particular problem, 4 arrows, 1 in each direction. Yeah, so there you go. Keep in mind that sometimes I draw this and then people start always drawing all 4 arrows. And the only reason you have to draw 4 arrows in this one is because there's 4 forces, 1 in each direction. If you have a problem where there's no forces left or right, then just don't draw any arrows left or right, and that's it. Okay, so moving on. This time you're basically working backwards. It says Gus slides a 60 kilogram copy machine from rest. So here's the copy machine. It's 60 kilograms. Gravity is going to pull it down with a force of 600 newtons. Gus is sliding it to the left from rest, so our initial velocity is going to be 0. He's pushing with 270 newtons, so here's our force of Gus. I'm going to write out his name so that it doesn't get confused with gravity. Don't forget to make it negative. The acceleration is 2 meters per second squared, so I can find my net force. He's sliding it to the left, right? So that means this acceleration should be negative, right? Because it's going to accelerate this way, right? So my net force is going to be negative 120 newtons. So that means there's going to be friction slowing it down, right? Because otherwise I'd have a net force of 270. So there's got to be a force of friction to slow down the acceleration. There also, incidentally, needs to be a normal force, right? Because it's not going to move up or down at all. So my normal force is going to be positive 600 newtons. And so now the question is, what does friction have to be? So we're going to go net force equals force of Gus plus the force of friction. Negative 120 equals negative 270 plus the force of friction. So add 270 to both sides, and you get 150 newtons equals the force of friction. All right, there you go. All right, finally, in this one, you've got a constant velocity. I'm going to do this one really quick because I want to make sure I get to the terminal velocity problems. Constant velocity, right? So here's your box. You're going to have gravity, which in this one's going to be negative 1,500 newtons. You're going to have a normal force that prevents it from falling, 1,500 newtons. Since it's going at a constant velocity, your net force has got to be 0, which means that Sam's force is going to be one way. It doesn't give a direction, so let's just have Sam push this way with 540 newtons. Since your net force is 0, that means your force of friction is also got to be 540. And you know that your acceleration is 0, and your velocity is 4 meters a second. That away. Okay. All right, parachuting pig. So here we go. Here's our pig. All right, he's got a mass of 40 kilograms. So gravity is going to pull him down with a force of 400 newtons. There's air resistance. So what's happening now is the pig is falling down. Air resistance is going to try to slow down his motion. So here's your force of air resistance. It's going to be 240 newtons, right? And that's it, right? There's no friction because he's not touching anything. Nobody's holding the pig, so there's no other forces. So our net force is just going to be the 400 newtons from gravity, negative 240 newtons from air resistance. So you're going to get a net force of negative 160 newtons. So acceleration is net force over mass. So the acceleration is negative 4 meters a second squared. Okay. So the big thing I want you to notice here is if there wasn't air resistance, the pig's acceleration would be negative 10 meters a second squared, right? Because he'd be in free fall. So what's happening is the air resistance is giving the pig a smaller acceleration than gravity would, or technically less negative, right? So he is still falling down, just not as quickly as he would be if there wasn't air resistance. Now, an interesting thing happens here. As the pig, it turns out that air resistance depends on a few things, the size and shape of the pig, density, that kind of thing, but also it depends on the speed of the pig. So this pig is accelerating downwards, and it turns out, and this you want to write this down, the faster an object moves, the greater the force of air resistance. Write that down. The faster an object moves, the greater the force of air resistance. So what's going to happen in this problem is our pig is moving down, and as he continues to accelerate down, he goes down faster and faster and faster. And as he goes down faster and faster, your air resistance will get bigger and bigger and bigger. All right? And eventually, what happens is you reach what's called terminal velocity. Okay? So let me write down what terminal velocity is. Okay, so here's the deal with terminal velocity. As the object moves faster and faster, the force of air resistance gets bigger and bigger. You've seen that anytime you've put your hand out the window of a car, right? The faster you're going, the more wind you feel pushing your hand. So if the object is falling and there's air resistance, then as it falls, it goes faster and faster, causing the air resistance to get bigger and bigger, causing the net force to get closer and closer to zero until eventually the object stops accelerating. The velocity this occurs at is called terminal velocity. So write that down. Now that you've done that, I'm going to move this thing out of my way so we can talk about this. So here we go. Here's our cow. Cow, 400 kilograms. So the idea is gravity's pulling the cow down with 4,000 newtons, right? So what happens is, as the cow falls, he goes faster and faster. And as he goes faster, your air resistance gets bigger and bigger. So after he's fallen for a little bit, your air resistance is 1,000 newtons. There's still a downwards net force, so the cow is going to keep speeding up. So your air resistance will get bigger. Eventually, it'll be 2,000. There's still a downward net force. The cow keeps accelerating downwards. Air resistance gets bigger. Eventually, it hits 3,000. Cow still being pulled down. There's still more force pulling him down. He's going to keep accelerating. Air resistance gets bigger and bigger and bigger and bigger and bigger until eventually the force of air resistance exactly equals the force of gravity. And at this point, the cow will stop accelerating. So now he has no acceleration, he has a net force of 0, and he's going to just fall at a constant velocity. Okay? Now, the terminal velocity for different objects is different. Like I said, it depends on the weight of the object, it depends on size and shape of the object. When you open up a parachute, what you're doing is you're making your terminal velocity lower because your air resistance gets bigger quicker because there's more surface area catching the parachute. So anyway, that's terminal velocity. I'm going to stop there since I went over my 15 minutes, but I'm under 20. I think that's it. Cool. Have a good one.